Okay, so we want to talk about additive rules for probability, right? So before we get into the additive rules, what I will do is I'm gonna do a quick review of the probability theory that you would have seen with Miss Bhutan, right? Okay, so by now you should know what an event is, right? An event is a subset of a sample space, right? And what we want to do is we want to get or what we want to do is we want to calculate probabilities of events, right? Okay, so a very simple case is if we toss a coin, a fair coin, right? And we toss it once, right? So a sample space is a set of possible outcomes for this experiment, and the sample space would be either heads or tails, right? Okay, so the fact that this coin is fair, right, means that the probability of getting a head is a half, and the probability of getting a tail is a half, right? You want to notice is if we're saying that the probability of the head is a half and the probability of a tail is a half, right? We're actually making certain assumptions there, right? So we're making certain assumptions about the probabilities, right? The assumption that we're making, well, one assumption that we're making is that the coin, because the coin is fair, the probability of a head is equal to the probability of a tail, right? So that's one assumption that we're making, right? The second assumption that we're going to make over here, right, is we're making the assumption that the probabilities add to 1, right? So this is what I have stated in the notes about probability values for a sample space, a finite sample space, okay? Okay, so finite sample space means that the amount of outcomes in your sample space is a finite number. It's not infinite, right? Okay, so we make an assumption, first of all, as I said, that because the coin is fair, probability of each outcome is equally likely, right? So probability, each outcome is equally likely, so the probability of each outcome is the same, right? And the second assumption that you're making is that the sum of the probabilities it's equal to 1. So if both of these equally have the same probability and they sum to 1, right? What that means is that each probability is a half, right? Okay, and then, well, next assumption that you making over here, right, is that the probabilities can never be negative, right? Okay, right, so that's what's stated over here, right? And but implicitly, people usually just assume these things, right? But it's good to know that you're actually assuming it, right? Okay, so you want the event of obtaining a head, right, is this subset here H, and the probability of getting uh, getting a head, right? So the probability of obtaining a head, right, is equal to a half, right? Okay, so let's do a next example of that, right? So a next example is slightly more complicated. Is we have a fair coin and we flip it twice, right? Okay, and what we want is the probability of at least one tail, right? Okay, so in this case, your sample space consists of 4 elements, right? Because if you toss it twice, for example, you can get head, 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 tail, tail, head, or tail, tail, right? Okay, so because the coin is fair, right? Each of these 4 outcomes is equally likely, right? And because the probabilities have to sum to 1, right? What that would mean is that each one, each possible outcome over here would have a probability of a quarter, right? Okay, right. Now, what we want is probability of at least one tail, right? So first we find the event of at least one tail. And the event of at least one tail is the subspace of the samples, subset of the sample space that satisfies this condition at least one tail, right? So what you do is you look in your sample space and you see, well, okay, it's at least one tail is head tail, tail head, or tail tail, right? So this is the event over here, right? And to get the probability of this event, what you do is to get the probability of this event, you add the probabilities for each of these outcomes over here, right? Okay, so the probability of this event, which is head tail, tail head, and tail tail, right? To work out this probability, you add the probabilities for each of the outcomes, and so you get a quarter here, you get a quarter here, a quarter here, and you get 3/4 here, right? A little more formally, the probability of an event, right? And this is an event where you have a finite number of elements in this event, right? The probability of such an event is the sum of the probabilities of all the outcomes in the event, right? So the example that we just looked at, the event over here was the event of at least one tail. This event had 3 outcomes in it, and the probability of this event is the sum of all the sum of the probabilities of each of the outcomes, right? So this outcome had tail, you have this probability, tail head, you have this probability, tail tail, you have this probability, and the probability of the event, which consists of these 3 outcomes, is the sum of the probabilities for each outcome, which is 3/4, right? Okay, so if you have an event, right, and the event is of finite size, right, how you get the probability of the event is you really just add up the probabilities for each of the outcomes in the events, right? Okay, so let's do one more slightly more complicated example here, right? Okay, so well, this example here, what we have now is we have a die that is not fair, right? So it's biased, right? And an even number is twice as likely to occur as an odd number, right? Okay, what we want is the probability that we get a number less than 4 when we roll the die once, right? Okay, so for this die, well, what's the sample space, right? The sample space is 1 to 6, right? So when you roll the die, the amount of dots you're going to see on the top face would either be 1 dot, 2 dot, 3 dots, up to 6 dots, right? So the sample space we could write as 1 to 6 here, right? Okay, now what we want is probabilities for each of these outcomes, right? But now you're in a situation here where your probabilities are not equally likely, right? Because they tell you that even number is twice as likely to occur as an odd number, right? Okay, so how are we gonna, we still need to get the probability of this event occurring. We still need probabilities for each of the outcomes, right? So that's the first thing that we would need to find, right? Okay, so probabilities of each of the outcomes, well, what we're going to do is we're going to say, well, all right, the probability of this one over here, we're going to call it P, right? And the probability, well, of the even number, right, 2, right, is, as you see over here, even number is twice as likely to occur as an odd number. So the probability of the 2 is going to be 2P, right? Okay, and we're assuming that the odd numbers are all, if you have 1, 3, and 5, you're equally likely to get 1, 3, and 5. So the probability of the 3 over here is P. Likewise, the probability of the 4, because it's even, is 2P. Probability of the 5 is P, and probability of the 6 is 2P. Right? Okay, right, so these are the probabilities of each of your outcomes, right? And these probabilities, they have to sum to 1, right? Okay, so your probabilities over here, they sum to 1, right? So you add up all of these, right? And when you add P plus 2P plus P, 2P plus P plus 2P, right? What you get is 9P on this side, right? So the 9P is equal to 1. And that tells me that P is equal to 1/9, right? Okay, so now I know, well, okay, the probability of obtaining the 1 is 1/9, and the probability of 2, for example, is 2/9 over here, right? And with that assignment, notice that the probabilities, they're going to all add. If you add up all the probabilities for your outcome, it's going to come to 1, right? Okay, so now let's answer the question, right? We want the probability that we get a number less than 4, right? So the event of a number less than 4 is a subset of my sample space, which is 1, 2, 3. And what we want now is we want the probability of this event, right? Now remember what the probability of an event is when the event is of a finite size, right? What you do is you really just add up the probabilities for each of the outcomes. So probability of the E occurring over here is probability of 1 plus probability of 2 plus probability of 3. Right, remember the probability of 1 is 1/9, probability of 2 is 2/9, and probability of 3 is 1/9. So the sum of these probabilities is 4/9, right? Okay, so your answer over here, the probability of obtaining a number less than 4 is in fact 4/9, right? Okay, so for the same problem over here, right, let's consider the probability of a different event, right? So we roll in a die once, the die is unfair such that the even number is twice as likely to occur as the odd number. And what we did is we worked out the probabilities for each of the outcome. In particular, the probability of the 1 is 1/9 and the probability of the 2 is 2/9, right? Probability of 3 is 1/9, probability of 4 is 2/9, right? Okay, so we're considering a different event now, and this is the event of obtaining an even number, right? Okay, so this event of obtaining an even number is set of outcomes that consist of this event would be 2, 4, and 6, right? Okay, so notice this is a different event, different subset of a sample space. It's not the same as this event E over here. But we could still find the probability of this event A, right? And how you find the probability of this event A is you add the probabilities for each of these outcomes, 2, 4, and 6, right? And for each of these, the probability is 2/9. So your probability of obtaining an even number is 2/3, right? Okay, and for any event of this sample space, right? Any event B, which I'm gonna call B over here, I can calculate the probability of that event, right? By just adding up the probabilities of each of the outcomes, right? Okay, so what that means is that for any subset, any event of the sample space, I can get a probability, right? I can assign a probability, right? Okay, so what you're doing is any event, any subset here, you assign in a probability to the event B. You can compute P of B, right? Okay, so you can calculate probability of B, right? Okay, so this, if you want, this is a function on the subsets of your sample space, right? And for each subset, you're gonna get a probability, right? And something like that is called a function, right? So this is for each subset, you have a function that will give you a probability. So for example, for this subset over here, 2, 4, 6, right? The function p, right, will give you the probability 2/3, right? For this subset over here, the function p, right, the probability function will give you a probability of 4/9, right? So for each subset of my sample space, I'm gonna get a probability, and if you look at it that way, what this is this is a probability function on the events of your sample space, right? So any event or any subset over here, you can get a probability. You can assign a value, and once you assign in a value, that is what you call a function, right? Assuming that you assign it in a systematic manner, right? Okay, so you could regard this p over here as a probability function. This method of calculating probabilities is a probability function on the events of the sample space, right? Okay, so why I care about that is your axioms of probability are defined in terms of a probability function. All right, so we just saw an example of a probability function for a particular sample space, right? Okay. All right, so as I said, we're gonna use the idea of a probability function to talk about axioms of probability, right? Okay, so probability function is a rule that associates a unique number to any event of a sample space, right? So we just saw that, right? If I have an event over here, for example, this event, right? This event, I can determine the probability of it, right? And for any event in my sample space, right? And the sample space that we were talking about was sample space that we were talking about in the previous example. This was my sample space, right? Okay, so for any event in my sample space, I can determine a probability, right? So that's an example. That is what a probability function means. Any event you can get a probability. So the p over here is a probability function, right? And this is what this definition is saying, right? Any event A over here, I can determine a probability, right? Okay, so it's not just that it determines a probability function also needs to satisfy axioms of probability, right? So the axioms of probability are these three axioms over here, right? Three axioms is that probability of any event has to be bigger than zero, right? In other words, you can't have negative probabilities for an event. Right, so probability is sample space being equal to 1, right? Probability the S equal to 1. What this means is that this means the probability of something happening is equal to 1, right? And if you roll your die, one of these must happen, right? So if you have your entire S over here, probability of S occurring, right, means that probability that one of these occur, right? And one of these must occur, right? Okay, so therefore you get your maximum probability over here of 1, right? Okay, now your third condition, your third probability axiom here is that if you have disjoint events, then the probability of the union of disjoint events is the sum of the probabilities, right? So this notation may be a little confusing, so let me give you some easier examples, right? Okay, so if I have two disjoint events such as A1 and A2, right? Then the probability of the union of those events, right, is equal to the sum of their probabilities, right? And a simple example over here, right? So we're using again the example with this loaded die, where this is my sample space. The sample space is 1 to 6, right? We worked out the probabilities for each of these, right? And if I have considered two events over here of the sample space, which is one is 2, 4, 6, so one is even results, and this second event over here, which is B, consists of getting an odd result, right? Okay, so these are disjoint events, right? You have nothing in common with A and B over here with these events, so the intersection over here is empty, right? Okay, so A and B are disjoint, right? Now, what we want to do is we want to check if this is true, right? That probability of the union of the events is equal to the sum of the probabilities, right? Okay, so well, what's the union of A and B over here, right? The union of A and B is, well, it turns out in this case the union of A and B is just the entire set S over here, right? Okay, so the probability of A union B is equal to, and we just figured out what A union B, this A union B is S, so the probability of S is equal to 1, right? Okay, so that's working it out that way, but let's work out the individual probabilities, probability A and probability B, right? Okay, so what's probability of A? Probability of A is probability of 2 plus probability of 4 plus probability of 6. Remember, if you want to work out probability of an event, you add in the probabilities for each of the outcomes, and in this case over here, because you have a loaded die, right, the probability of an even number is 2/9, right? So this one is probability of the 2 is 2/9 plus 2/9 plus 2/9 gives you 6/9, which is the 2/3, right? And then the probability of the event of having an odd number is probability of 1 plus probability of 3 plus probability of 5. Okay, each one over here is 1/9, right? So when you add that up, you get 1/3. So probability of A is 2/3, probability of B is 1/3. And the sum of the probabilities is equal to 1, right? So this is an example of that probability, if A and B are disjoint, right, then probability of A union B is equal to the sum of the probabilities, right? Okay, so that's an example of this first one over here, right? If I have two disjoint events, the probability of the union of the events is equal to the sum of the probabilities, right? Likewise, if I have three disjoint events, the probability of the union of and disjoint over here means A1 intersect A2 is empty, A2 intersect A3 is empty, and A1 intersect A3 is also empty, right? Okay, right. So in the case of when I have three disjoint events, right, the probability of their union is equal to the sum of the probabilities, right? Okay. More generally, if I have n disjoint events, right, then and if I take the union of A1 to AN over here, which is on this left hand side, the probability of the union is equal to the sum of the probabilities of each event, right? Okay, so that is what is stated in that is what this over here means, right? This is union of this notation over here means what you're doing is you're taking the union of the AI's, so you're starting from I is equal to 1, so that's just A1. And then you go in I is equal to 2, which is this A2, and then you go up to I is equal to N, which is this AN over here, right? So this union over here, this sort of fancy looking union, is the union A1 to AN, right? And this is just summation notation, which means that's equal to this right hand side over here, right? So this statement over here is really just this statement that I have, this second to last displayed statement over here, right? It's just that I wrote out everything in this on the left hand side and the right hand side over here. Okay, and then this one over here, right? What this one here is saying is that if I have the union of disjoint events, but here I could potentially have a infinite, countably infinite collection of events, right? So I can have A1, A2, A3, A4, and I keep going, right? And if I take the union of those, right? So that's what this means over here. Then the probability of that union is equal to the sum of the probabilities of the A1, A2, and so on, right? And this here would be an infinite sum, right? Okay, so typically we're not really going to see this sort of thing over here, right? Most of the cases would be looking at a union of a finite number of events. Okay. Okay, so why you care about these axioms or probabilities, that you can use these to derive some useful results, right? So using these over here, I can obtain this result that if I have an event A, then the probability of A complement is equal to 1 minus probability of A. I can get that the probability of the empty event or the empty set is equal to 0. I can get that if A is a subset of B, then the probability of A is less than or equal to the probability of B, right? And then I have this one over here, right, that probability of A has to lie, of the probability of any event A has to lie between 0 and 1, right? That may be somewhat obvious and so, right, but it still requires a certain amount of proof, right? So let me give you an application of using this first statement here, that probability of A complement is equal to 1 minus probability of A, right? Why you want to use something like this is sometimes if you want to get probability of A, right, it's easier to work with the A complement than to work with the A, right? And this over here, this is an example of that, right? Okay, so I have an experiment that consists of tossing a fair coin 3 times, right? So we talked about that. Okay, so when we toss a when we toss a coin 3 times in succession, right? This would be the sample space that you get, right? Now, what we want is you want the probability of obtaining at least one head, right? Okay, so we could do it okay, so one probability of getting at least one head, which means that if we're going to do it probably in a normal way, right? What we would want is the event of obtaining at least one head, right? Which means that you'd need all the outcomes that that satisfy this condition of at least one head, right? Okay, now all of those would be the first 7 over here, right? So to do this, to get this event A, right, what you'd need to do is, okay, so if you want to get your event A over here, what you need to do is you'd need to first find a sample space probably, and then list all these 7 over here, right? Okay, and then you work out your probability for that, right? Okay, so you could probably do it in this case if it was you tossing the coin 3 times, right? But if you say tossing the coin, say 10 times or so, that would actually be fairly difficult to do, right? Because you'd have a lot of results over here, right? So probably the more efficient way to do this problem, right, is to consider the complement, right? So what's the complement of obtaining at least one head, right? Well, the complement of obtaining at least one head, right, is the event of obtaining no head, right? Okay, and notice the event of obtaining no head is easy to specify what that event is, right? Uh, the event of obtaining no heads, it means that you just have three tails, right? Okay, right, so B is the complement of A. Well, how can you check that, right? Well, you can see that well, A union B is equal to S, right? And then A intersect B is equal to the empty set, right? Or you could really just look over here. This here is B over here. Three tails is B, right? And at least one head is the other seven, right? So B is the complement of A with respect to your sample space S, right? Okay, so what we can do is we can use the fact that since B is the complement of A, right? Uh, we have that probability of A is equal to 1 minus probability of B. Okay, so I have this stated as probability A complement is equal to 1 minus probability of A, but you could also, from this here, you have probability of A is equal to 1 minus probability A complement. So that's what I use over here. What I want is probability of A, right? So probability of A is 1 minus probability of A complement, and B is A complement. Okay, and the probability of B occurring is the probability of obtaining exactly three tails, right? So, and because your sample space has 8 elements in it, right? And each outcome is equally likely, right? And the probability of this outcome occurring is 1/8, right? So overall, what you get is that probability of A is 1 minus the probability of the complement, right? So 1 minus 1/8, and your answer is 7/8, right? Okay, so these results are somewhat useful. In particular, this one relating the probability of A to A complement is something that we're going to use all the time. All right, so we just saw that if we have two disjoint events such as A and B, right, then the probability of A union B is equal to probability of A plus probability of B, right? So that's the same statement over here. Here the events are called A1 and A2, right? And the probability of disjoint A1 and A2 is equal to probability of A1 plus probability of A2, right? Okay, so now what we want to do is we want to consider when the A and B are not disjoint, right? So the A and B have a non-empty intersection, right? Okay, so in that case, the probability of, if I have A and B, the two events here, right? Then probability of A union B is equal to probability of A plus probability of B minus the probability of A intersect B, right? Okay, so notice this is stated for any two events over here, right? And this statement over here, this proposition would also work in the case when A and B are disjoint, right? Because when A and B are disjoint, what would happen is that what you'd have over here is the empty set, and we just saw that probability of the empty set is equal to 0, right? So if A and B are disjoint, you're not going to have this over here, and you're just going to get back to statement 1, right? Anyway, the point is that this over here, if you want, is probably a better statement because this could handle any events, right? A and B, whether they're disjoint or not, right? Okay, so let's see an example of using this here, right? Okay, so consider this experiment where we toss a die but twice in succession, right? So the sort of results that we're going to get would look like this, right? We can get, say, 1 on the first throw, 1 on the second throw, right? Or we can get 2 on the first throw and 1 on the second throw, right? And you want to notice, well, what you have is 36 possible results over here, right? So your sample space is of size 36, right? Okay, and what we have is the event of a 6 showing on the first throw, right? So you see over here what the A is over here, right? The A is consists of uh, those outcomes that are in your red shape over here, right? Okay, and B is the event 6 shows on the second row, right? So that would be D6 over here, and that's in your green circle over here, right? Okay, so this is the event A in red, and B is the event B in green, right? And what we want to get is probability of A and probability of B, probability of A intersect B and probability A union B, right? Okay, what's probability of A? Alright, so in your event A over here, you have 6 outcomes, right? Okay, and this die is fair, right? Which means that each of these outcomes are equally likely, right? So you have 36 outcomes in your sample space. Each one is equally likely. So probabilities have to sum to 1. So what that means is that each probability of a single outcome is 1 on 36, right? Okay, so your probability of A is 6 on 36, right? Or next way of looking at this is that you have 36 possible outcomes over here, right? And the size of your total number of possible outcomes is 36. The size of your sample space is equal to 6, right? And when you have equally likely outcomes, the probability of your event is number of outcomes in your event over the total number of outcomes. So you get 6 on 36, which is 1 on 6, right? Okay, so the probability of A is 1 on 6, right? Now, likewise, B has 6 outcomes in it, right? So the probability of B is the number of outcomes in B over the total number of outcomes, which is 1 on 36, right? Okay, so what's A intersect B over here, right? A intersect B is this 6, 6 here, right? So you have a single outcome in A intersect B, right? So that event just consists of one outcome. So your probability of that event is number of outcomes in the event, which is 1, over the total number of outcomes, which is 36. Okay. Okay, so your probability of A intersect B is 1 on 36. Alright, so now what I want is probability of A union B, right? Now what is A union B over here, right? Okay, so this is A over here consisting of the 6 elements, and B over here consisting of these 6 elements, right? But what you want to notice is that overall A union B, right, has these 6 on the bottom and 5 more, right? So you don't want to double count the 6, 6, right? So A union B, in fact, actually has 11 elements, right? Okay, so let's just notice that, right? But anyway, so if I want probability of A union B, I can use this formula here, right? Now the probability of A is giving me the probability of this event occurring, which is 6 on 36. Probability of B is probability of this event occurring, which is 6 on 36, right? But you really can't just add both of these and expect to get the correct answer, because what you're doing is a double count in this 6, 6 here, right? Okay, so because you don't want double count, right? What you do is, if you have probability of A and probability of B, what you did is you counted this 6, 6 twice, right? So you need to subtract off your double count over here, right? So you get 6 on 36, 36. 6 on 36 for probability of A, 6 on 36 for probability of B, and then you subtract your double count, which is the intersection over here, right? So minus probability of A intersect B, and probability of A intersect B is 1 on 36. So this would give you your answer over here, which is 11 on 36, right? Okay, so the point that I want to make in this example is probability of A union B is equal to probability A probability B, right? Minus probability A intersect B. What you're doing over here is you're subtracting double count if you want, right? The fancier name for this is inclusion exclusion, right? Okay, so well, that's what it's called, right? Inclusion exclusion is when you subtract off extraneous elements from a calculation. Alright, so we saw that probability A union B is equal to probability A plus probability B minus probability A intersect B, right? Okay, so in the case of when we have three events A, B, and C, we have a similar result, right? So notice over here what I did is to get probability A union B, I added probability A to probability B, and I subtracted off the intersection to avoid double counting, right? So similarly for probability of the union of three events, it's probability of A plus probability of B plus probability of C, right? Okay, so you're gonna add the probability, so probability of A plus probability of B plus probability of C, right? You subtract off the intersections, prevent the double counting, but doing this if you want when you subtract off all of this, right? You subtract off too much, right? So what you need to do is you need to actually add back the intersection of all three, right? Now that's a pretty informal description of what's going on, right? And if you want a proof, the proof is in the notes, right? Okay. But anyway, so this is the result for probability of the union of three events, right? You add the probabilities of the A, B, and C, you subtract off the intersection of 2, and then finally you add back the intersection of 3, right? Alright, so now let's consider something called conditional probability, right? Okay, so I have an experiment, and an experiment with sample space S, and two events in that sample space, right? Okay, what I want is the probability of B occurring given that the event A has already occurred, right? And the probability of B occurring given that A has already occurred, right, is called a conditional probability, and it's denoted by a B with this vertical slash A, right? So how you read this is probability of B given that A has occurred, right? Alright, now the good thing about this conditional probability is there's a way to calculate it given what we already know, right? So if we want the probability of B given that A has occurred, right, that probability is the probability of A intersect B divided by the probability of A, right? Now this formula is only going to make sense provided that your probability of A is bigger than 0, right? Alright, so let's see an example of calculating a conditional probability, right? Okay, so we have a fair die that is thrown twice in succession, right? Okay, so if it's thrown twice in succession, these are what your outcomes are going to look like, such as this 1, 1, 2, 1, and so, right? So remember, this 2, 1 means that you got 2 on the first throw and 1 on the second throw, right? Okay, and then your sample space for this sort of situation, which we just saw, right? The sample space when if you throw a dice twice in succession, right? Your sample space would consist of 36 pairs like this, right? Okay, so you're told that 6 has shown on at least one of the throws, right? Right. So what you're told is you're told that a 6 has occurred, right, on at least one of the throws, right? You want, so this event has already occurred, right? The event that 6 is showing on at least one of the throws, that event is occurring, right? So that's what we're going to call the event A, right, in this definition, right? So A has already occurred. We're going to call that A, right? And what we want is the probability that the first throw is a 6, right? So what they're asking you to do is find the probability that the first throw is a 6, given that 6 is showing on at least one of the throws, right? Okay, so you have two events here, A and B. A has already occurred, and what you want is the probability of B given that A has occurred, right? So the one that has already occurred So the one that has already occurred is A, right? That 6 shows on at least one throw, right? So this red curve over here encloses all the outcomes that belong to the event A, right? So notice here 1, 6 is 6 showing on at least one throw, right? 3, 6 over here is 6 showing on at least one throw. Likewise, 6-1 also lies in the event A, right? And 6-6 also, right? Because you say at least one throw, so it is possible that you could have a 6-1 on both throws, right? Okay, so A consists of 11 outcomes from your sample space, right? Now, what is B, right, in this setup, right? Because you're going to be using a conditional probability, right? So we want probability that B, which is the first row, is a 6, given that 6 is showing on at least one of the throws, right? Okay, so B in this case is 6 showing on the first throw, right? And the event of B, right, is 6 on the first throw, which is these 6 outcomes in the green curve here, right? Okay, so what we want is probability of B given that A has occurred, right? Okay, so we could actually just work it out, right, using our definition over here, right? So what's probability A intersect B, right? Okay, so we want the definition, we want probability of B given A, right? So we want this conditional probability. How we calculate conditional probability is probability A intersect B divided by probability of A, right? Okay, right, so what we would need is we'd need probability of A intersect B, right? Okay, so what's probability of A intersect B, right? So this is B over here and this is A over here. Notice B is contained inside A, right? So A intersect B is really just B over here, and the probability of A intersect B is number of outcomes in this intersection, which is 6, over the number of outcomes in your sample space, which is 36. Remember, we're assuming that the outcomes over here are equally likely, right? Okay, so probability of A intersect B, right, is 6 on 36. And the probability of A occurring, there's 11 outcomes in A, right? So the probability of A occurring is 11 on 36, right? Okay, so your conditional probability, according to our definition over here, is probability A intersect B divided by probability of A, which is 6 on 36 divided by 11 on 36, which is 6 on 11, right? Alright, so one way to look at this conditional probability is, okay, so let's compare, say, probability of B to probability of B given A, right? Okay, so what's the probability of B, right? The probability of B by itself is just 6, right? There's 6 outcomes in B, right? And there's 36 total outcomes in S. So the probability of B occurring would be in fact 1 on 6, right? So that's the probability of B, right? But what's the probability of B given that A has occurred, right? Now, the fact that A has occurred means that what you're doing is you're reducing your total amount of possible outcomes, right, to now these 11 over here, right? And in this particular case where B is contained in A, right, the probability of B occurring given that A has occurred, right, is in fact 6 out of the 11, right? So probability of B occurring given that A has occurred is probability that one of these 6 occurring out of the 11, right? So it's 6 on 11, right? So let's start to consider the idea of independence, right? So before we get a formal definition of independence, let's note what probability of B is, right? And I just talked about that, right? So probability of B occurring, you have 6 outcomes in your event for B, right? So probability of B occurring is 6 on 36, right? And the probability of B given that A occurred, right, is 6 on 11, right? So your conditional probability of B given that A has occurred is 6 on 11, right? Okay, so what you want to notice is that your conditional probability of B occurring given that A has occurred is not equal to the probability of B, right? Okay, so what that indicates is that the occurrence of A actually influences the occurrence of event B, right? Okay, but however, there are situations where you're gonna have events A and B, not this one, where not this example here, where probability of B given that A has occurred is actually equal to probability of B, right? So in this situation over here, that even if A occurred, right, it doesn't affect the occurrence of B, right? It doesn't change the probability, right? Okay, so the occurrence of event A has no impact on the probability of the occurrence of event B, right? Okay, and in terms of probability, what we're going to see is that it's a certain sort of proportion is maintained, right? Okay, but it's easier if you see that with an example. Anyway, so if you have this situation with events A and B, right, and the probability of B occurring given that A has occurred is equal to probability of B. In other words, the occurrence of A doesn't change the probability of B occurring, then what you say is that A and B are independent, right? So your definition of independence is that two events A and B are independent if the conditional probability of B given that A has occurred is equal to probability B, or that probability A given B has occurred is equal to probability A, right? So there's an error in these notes here. There should be probability A over here, right? And that's assuming the existence of the conditional probabilities, right? Now you want to remember that your conditional probabilities are defined using a fraction like this, right? So it is possible that your conditional probabilities may not exist, right? Okay, so when you're using this definition over here, right, you're making the assumption that the conditional probability exists, right? Okay, so events A and B are independent if probability B given A is equal to probability B, or if probability A given B is equal to probability of A, right? So as I said, there's an error here. There should be probability A, right? Okay, and if you do not have equality for these, right, then what that implies is that the A and B are actually dependent, right? Okay, so this example over here where I have this is event A and this is event B. These events A and B are not independent, right? Okay, so typically you say not independent and rather than dependent. Okay, but either one would work. All right, so let's look at this example here, which will give us example of two independent events A and B, right? Okay, so we have a single card drawn from a deck of 52 cards, right? So you see an illustration of your 52 cards here, right? A is the event of choosing a heart, and B is the event of choosing a face card, right? And we want to show that A and B are independent events, right? Okay, so to show that A and B are independent events, we can use this condition here that the probability of B given A has occurred is equal to probability of B, right? Okay, so how we show this is that we just calculate each of these separately, right? Okay, so what's the probability of obtaining a face card, right? Well, you have by face card they mean jack, queens, and king, right? So an ace doesn't count as a face card, right? Okay, so how many face cards do you have? Well, you have 3 of them for each suit, right? So you're going to have 3 times 4, 12 face cards, right? And so the event B, right, would consist of 12 occurrences here, right? And the probability of B occurring is the number of outcomes in your event over the total number of outcomes in your sample space. In other words, the number of face cards, which is 12, right, over your total number of cards, which is 52, right? So what you get is you get 3 on 13, right? Okay, so that's the probability of B, right? And now what we want is conditional probability, right? So for a conditional probability, what we need to remember your definition of conditional probability is probability of B given A has occurred, right? And that's how you calculate it, is probability A intersect B over probability of A, right? Okay, so what is the intersection? Well, let's first work out what's probability of A, right? A is the event of obtaining a heart, right? Now you have 52 cards, 13 of which would be hearts, right? So the probability of getting a heart is going to be number of hearts over the total number of cards, which is 13 on 52, right? Okay, and the probability of A intersect B, right? This means that, well, A means that the card needs to be a heart, and B means that it needs to be a face card, right? So what you're looking at is face cards that are actually hearts, and you have three of those, right? So probability of A and B occurring, right? A intersect B is the amount of occurrences in A intersect B, which is 3 over here, right? So number of face cards that are hearts over total number of cards, right? So probability of A intersect B is in fact 3 on 52, right? So your conditional probability over here would be 3 on 52 probability A intersect B divided by probability of A, right? And that's 3 on 52 divided by 13 on 52, which is 3 on 13, right? And what you want to notice is that your conditional probability B given A is in fact equal to the probability of B, right? So in this case, your events A and B are independent, right? Okay, all right, so that's your calculation, right? Your calculation in fact shows that events A and B are independent, right? But let's see if we could get an idea what's happening from the diagram, right? From this diagram over here, right? Okay, so what's probability of B, right? Probability of B is having face cards, right? Now, having face cards means that there's for each suit there's 3 out of 13 face cards, right? So if you have your 4 suits, notice you have your 12 face cards over here. So probability of B is the 12 out of the 52, right? Now what you're doing is you're considering the conditional probability over here. Okay, now the probability of, let's go back to the probability of getting the face card. So the probability of the face card is 12 on there over there, the 52, right? And notice your proportion there. The proportion of 12 for 52 is in fact 3 out of the 13, right? Okay, now if you restrict yourself to just hearts, right? So you're considering a conditional probability here. It means now you assume that you already chose a heart and you want to see what's the probability of getting a face card, right? So that would be 3 out of the 13 here, right? Now the point is that I want to make is that if you impose the condition A over here, right? The proportion of face cards for the number of cards that you're choosing from actually remains the same, right? So in the case of when it's the B, right, just choosing the face card, it's the 12 from the 52, right? But now if you impose the condition A over here, right, it is the same proportion, right? It's the same 3 out of 13 over here, right? So your independence really has to do with the fact that when you impose the condition A over here, you actually maintain the proportion, right? Okay, so one more time, the event probability of B event occurring is in fact a certain proportion relative to the sample space, right? And the proportion was 3 out of 13, right? And total number of cards is 12 out of 52, right? Okay, if you impose the condition that it must be a heart, right, you still maintaining the same proportion of getting a face card, right? So now the probability of getting a face card is 3 on 13, right? So independence of events, right, has to do with a certain type of product structure, right? If A and B are independent, when you impose A upon B, right, you actually maintain the same proportion, right? Okay, so that is a rough idea of how you can look at independence, right? A and B are independent means that if you impose A on the condition B, you still maintain the proportion. Alright, so we saw what the definition of conditional probability is, right? The probability of B given that A has occurred is equal to probability of A intersect B divided by probability of A, right? Okay, now if your probability of A is right, so with this expression over here, what you can do is you can just multiply throughout by probability of A, right? So if I multiply on both sides over here by probability of A, right, what I will get is probability A intersect B is equal to probability A times probability of B given that A has occurred, right? Okay, so in a sense, all you're doing is you're just rearranging the definition of conditional probability over here, right? And for this to be to make sense, to be well defined, right, you want your probability of A to be bigger than 0, right? Okay, so this is called product rule, right? To get the probability of A intersect B, right? What you could do is you take a probability of A and multiply it by a conditional probability of probability B, given that A has occurred, right? Okay, now this over here, this comes in pretty handy when we're doing problems with Bayes' theorem and so on, the tree diagrams, right? Okay, so this is fairly useful for us, right? Okay, so let's use this product rule to work out this example over here, right? Now this example, we could work out in a variety of ways, right? You could in fact use combinations or permutations to work this out, right? But what we want to do is we want to use this product rule, right? Okay, so we have a fuse box, 20 fuses, 5 of which are defective, right? And we're choosing 2 fuses in succession without replacement, right? Okay, so what we want is the probability that both fuses are defective, right? So what we say is we're going to let A be the event that the first fuse is defective, B be the event that second fuse is defective, right? And probability that both fuses are defective are the probability of the intersection of A and B, right? So that's the event that first and second fuses are defective, right? Okay, so to work out the probability of the intersection of these events, right, what we're going to do is we're going to use this product rule here, right? So probability A intersect B is equal to probability A times probability B given A, right? Alright, so first of all, well, what's the probability of A, right? So that's A is when I'm choosing the first fuse, right? So I'm choosing one fuse out of 20, and we want a probability that that first fuse is defective. So you have 5 defective out of 20, so the probability of that first one being defective is 5 out of 20, right? Okay, now the second, we want a conditional probability over here. So this is the probability of second fuse is defective given that the first fuse was defective. The first fuse that you chose was defective, right? Now you're choosing in succession without replacement, right? Okay, which means that when you chose the first fuse, you didn't replace it, right? So when you chose the first fuse, right, you have 19 overall remaining, and 4 of those are defective, right? So the probability that now when you choose your second fuse that you get a defective one, given that the first one that you chose was defective, right? The probability of that occurring is 4 on 19, right? So your conditional probability here is 4 on 19. So probability A intersect B is probability of A multiplied by a conditional. So it's 5 on 20 times 4 on 19, which is 1 on 19. That events A and B are independent. We saw this definition for independence, that A and B are independent if conditional probability of B given A is equal to normal probability of B, right? Or probability of A given B is equal to probability of A, right? So remember there's a typo here, right? Okay, so what we want is a next condition for independence, to check for independence, and this is one that you may have seen before, right? That probability A and B are independent if the probability of the intersection of A and B is equal to probability A times probability B, right? Okay, so let me just sort of quickly explain where this comes from, right? The detailed proof is in the notes where I split into 2 cases, but I'll just consider the case over here when probability A is bigger than 0, right? Okay, so probability A is bigger than 0, right? Okay, so what do I want to show, right? What I want to show is probability A intersect B is equal to probability A times probability B, right? Okay, so what I'm going to do is I'm going to use my product rule, right? That probability A intersect B is equal to probability A times probability B given A, right? And I'm assuming that probability A is bigger than 0, so this conditional probability exists, right? Now, the fact that A and B, okay, so I want to show that if A and B are independent, then probability A intersect B is equal to probability A times probability B, right? Okay, right, so um, using your product rule over here and the fact that A and B are independent, right? So if A and B are independent, this probability B given A is just equal to probability B, right? So what I can do is I can really just replace this probability B given A by probability B. Okay, and that gives me what I want, right? Okay, so one more time, I want to show probability A intersect B is equal to probability A times probability B when A and B are independent, right? So I really just use my product rule over here. And if A and B are independent, it means that probability B given A is equal to probability B, right? Which means I could just replace this probability B given A by probability B, in which case I get probability A intersect B is equal to probability A times probability B. All right, so I have if events, okay, so I want to show if events A and B are independent, then A and B complement are independent. Similarly, A complement and B are independent, and A complement and B complement are independent, right? So this comes in handy when we do in calculations, right? So basically, if A and B are independent, then if I take a complement, I'm still going to maintain the independence, right? Okay, so what I'm going to do is I'm going to show part B over here, and the proofs of A and C are similar, right? Okay, so right, so to show part B over here, what I'm going to note is here I have A intersect B, which is this blue shaded area here, and here I have A complement intersect B, right? What I notice from the diagram is that the union of the blue shaded area and the green shaded area is actually equal to B, right? So A intersect B union A complement intersect B is equal to B, right? Okay, and what you also notice is that the blue area consists of elements from A, right? And the green area consists of elements from A complement, right? So they're not going to have anything in common, right? So the intersection of both of those is going to be empty, right? So what that means is this union is a disjoint union, right? There's nothing in common with the blue shaded area and the green shaded area, right? Okay, so now that I have this here, right, where the union on the right hand side is disjoint, right, what I do is take probability of both sides, right? So probability of B is equal to probability of this union, right? But these sets are disjoint, so that means that the probability union is the sum of the probabilities. This is a third probability axiom that I'm using. Okay, and once I have that, right, what I'm going to do is I'm going to rearrange, right? Okay, so I'm going to move this probability of A intersect B. I'm going to move it across on the left hand side and just rearrange, right? So what I have is probability A complement intersect B is equal to probability B minus probability A intersect B, right? Okay, now I'm assuming here that A and B are independent, right? So if A and B are independent, probability A intersect B is equal to probability A times probability B, right? And now what I do is I factor out probability of B, right? And here what I have is 1 minus probability of A, right? Okay, now 1 minus probability of A, you should remember we talked about that, is equal to probability A complement, okay? And what I just showed over here is that probability of A complement intersect B is equal to probability of A complement times probability of B, right? And that in fact shows that A complement and B are independent, right? because really what I'm doing now is I'm using this statement over here that to show that they're independent, right? So if I have events A complement and B, right? And if they satisfy that probability A complement intersect B is equal to probability A complement times B, then that means that they're independent,